Now let's discuss the definition of trigonometry. So trigonometry is a branch of mathematics, and the word is derived from three Greek words: tre, gonai, and metron. Tre stands for three, gonai stands for angles, and metron is for measurement. So it literally means the measurement of a triangle, because three angles is in what shape? Obviously, a triangle. So it's extensively used in business, engineering, astronomy, physical, and social sciences. Now, the concept of an angle is basically this: that you have two rays with a common starting angle, and it is called the initial side, and the point form an angle. One of the rays of an angle is called the initial side, and the other is the terminal side. So let's say this is the initial side, and since they're coming from a common starting angle, so this point, this is the terminal side, this line. The angle is basically identified by showing the direction of rotation from the initial side to the terminal side, and basically the angle is said to be positive if it is in anti-clockwise direction. So for example, if this point is A, this point is B, this point is O, this point is A, and this point is B. If this line OA is the initial side and this OB is the terminal side, obviously the direction of measurement of the angle is anti-clockwise, so it will be a positive angle. But if OB, this line OB is the initial side and OA is the terminal side, the direction will be clockwise, so that will be a negative angle. And angles are usually denoted by Greek letters such as alpha, beta, gamma, and theta, and we usually use this theta. Now let's see what a sexagesimal system is, and later on we'll see what the circular system is. So there are two ways to measure angles. One is the sexagesimal system and the other is the circular system. Let's discuss the sexagesimal system first. If the initial ray OA, so basically if we have this, so this OA basically means the direction is this from O till A, so this line. If the initial ray OA rotates anti-clockwise in direction in such a way that it coincides with itself, the angle then formed is said to be of 360 degrees. You may have heard of this, but just to explain, if we rotate this line in a circle, and once it completes a full rotation, obviously it will come back to its own self. So this complete rotation will be of 360 degrees. So basically, if you have this circle, and if this is the center, so let's say this is O, and this is basically A. So this line O to A, if you rotate it from A all the way back to where it reaches its own self, the circle is completed, and that is an angle of 360 degrees. So one rotation in the anti-clockwise direction, again, if you move this in the anti-clockwise direction, it will be 360 degrees because it's positive 360 degrees. If it went in a clockwise direction and reached its own self, it would be negative 360 degrees. Half rotation in the anti-clockwise direction is 180 degrees. Why? It's simple, because half of 360 is 180, and it is called a straight angle because basically if you rotate it halfway through, this becomes this, which is why it is a half angle, a straight angle. And a quarter rotation in the anti-clockwise direction, again, if you take a quarter of 360, it becomes 90, and it is called a right angle. So if you rotate this a quarter of the way, it reaches basically this point, and this angle, basically this angle, is of 90 degrees. Now, one rotation in the anti-clockwise direction, again, it's 360 degrees. 1 degree is equal to 60 minutes. So 1 degree a simple 1 degree turn can further be divided into 60 segments of 1 minute each, and 1 minute can further be divided into 60 seconds, just like in a clock, but like obviously. Basically, it's just further and further divisions to make things simpler. So, let's see what the definition of a circular system is. It's called radians. In the sexagesimal system, an angle was measured in degrees, minutes, and seconds. In a circular system, it's measured in radians. And it's just to make it simpler. Basically, it's another system of angle measurement, and it is mostly used for studying higher mathematics, and it's not really that complicated. Basically, in a circular system, 360 degrees rotation is basically equal to 2 pi, and that's how you just calculate it. You take a ratio and the relative ratio to convert from a a degree system to a circular system. Now let's express these sexagesimal measures of an angle in radians. So express the following sexagesimal measures of an angle in radians. So basically we need to convert 30 degrees in its radian form. Now 360 degrees is 2 pi, so again we use the same way by using ratios. So we basically have degrees ratio radians, and we already know that 180 degrees is pi radians, and we are given 30 degrees and we need to find it in radians. So we'll cross multiply, because again this is a direct relationship. So basically 180x is equal to 30 pi, and x is equal to 30 pi over 180, and that's exactly what we're doing here. So pi by 6 radians, simple. What is this? Now we're given 105 degrees, and again we have to convert it into radians, so we use the same method, and basically we'll end up with 7 pi by 12 radians. Simple, really. Now we need to convert 10 degrees and 15 minutes into radians. Again, 1 minute is basically the 60th part of a degree. So what is 15 minutes? Well, that's just 15 by 60 degrees. So we get 10 plus 1 by 4 degrees, which is just this, really, 41 degrees by 4. Now to convert it into radians, we'll use the same method as we did before, and we'll eventually end up with 41 pi by 720 radian. Now let's calculate the angle using length and radius. So we need to find theta when the length is 1.5 centimeters and the radius is 2.5 centimeter. Now remember this formula, that length is equal to radius into the angle. So theta is equal to length over radius, and that's just 1.5 over 2.5, so that now we have the angle as 0.6 radians. Remember that the value that you get here is in radians, not degrees, because we're dealing with a circle as it has a radius. Now say that you have a length of 3.2 meters and a radius of 2 meters. So again the same method, 3.2 divided by 2, so you get 1.6 radians as the angle. Now we need to find the measure of the angle. A circular wire of radius 6 centimeters cut, straightened, and then bent so as to lie among the circumference of the hoop of radius 24 centimeter. Find the measure of the angle which it subtends at the center of the hoop. Now we need to find theta, and we know that the radius is of 24 centimeters, and basically we need to find this theta. Now this is obviously the radius, and 12 pi centimeter is the circumference. So what do we do now? Length of the circular wire of radius 6 centimeter. Well, simple. L is equal to 2 pi r, so 2 pi into radius, and that means that now we have the length of 12 pi, which is why you have this 12 pi over here. Since basically we had initially a circular wire of radius 6 centimeters, so we'll use this 6 to find the total length of the wire. And now we need this entire 12 pi wire is subtended in a way that the angle from O, the center, is basically theta, and the radius, instead of being 6 centimeter, is 24 centimeter, because now we're not having the entire circle, it's just an arc. So 12 into 3.14, I mean that's just the value of pi, so that just gives you approximately 37.7 centimeters. Now we know that L is equal to r theta, and theta is equal to L over r, and we already know that the length was 37.7, and we already know that the radius is 24 centimeters. So that gives you an angle of 1.57 radians. Again, remember, in this formula, the angle theta must always be in radians. Now we need to find the area of a sector of a circular region. Show that the area of a sector of a circular region is of radius r. Well, there should be a space between this. Radius r is r square theta by 2. So we have to prove this. Now, where theta is the circular measure of the central angle of the sector. So let us consider a circle with the center at O. This is O, and this is the sector. Let r be the radius of the circle. So we have r over here, this, and this is also r because it's a circle, so equal lengths. And let L be the length of the arc AB. So let's say this is A and this is B. And let theta be the central angle in radians. So this is theta. We know that the area of the sector of a circle region is area of the circle is equal to the angle of sector ratio angle of circle. Now, what we mean by this is basically the area of sector of circular region over the area of the circle is equal to the angle of the sector over the angle of the circle. It's just like basically similar triangles or similar shapes. So basically, if you have this circle, and let's say you have this here sector, and this is a center, this center O, and this is the angle theta. Again, let me just draw it a bit larger. Just a second. I'm very sorry for this. Now, let's say that we have a circle here. And let's say we have an angle here. So, the entire area of the circle and the entire area of the sector, which is basically this term and this term, over the entire angle of the circle, which is just 2 pi, and the area of the sector, which is theta. So there is a direct relationship between these two. So the area of the sector, the area of sector of circular region over the area of circle is pi r square, is equal to theta over 2 pi, which is the angle of the circle. Now, you just use this and you eventually end up with this, and this is exactly what we had to prove. Now let's find the general angle also known as the coterminal angles. So the coterminal angles are the angles with the same initial and terminal side are called coterminal angles. If the angle is theta, then the rotation in the anticlockwise is theta plus 2 pi after 1 revolution, theta plus 4 pi after 2 revolutions. If the angle is theta, then the rotation in clockwise is theta minus 2 pi for 1 revolution and theta minus 4 pi after 2 revolutions. So just to explain what this really means is that if you have this line as the initial side and the terminal side, so basically it's just two lines overlapping, then the angle between them is just basically, well, theta. So I mean, but if you just rotate this entire line in a circle, sorry for the drawing, but like you get the point. If you turn it and it reaches the same point where both of these lines coincide with each other, that means that in the anti-clockwise direction, once you've gone all this way, it means that an entire 2 pi revolution has just occurred. So basically that just means it's theta plus 2 pi after one revolution. And if you rotate this again, it will be just theta plus 4 pi and again until basically it's become 6 pi, 8 pi, 10 pi, and basically just like that. So if you rotate this entire line in the anti-clockwise direction, so basically, basically like this, and then it reaches the same point where both sides coincide with each other, that means that you'll have theta minus 2 pi. So theta minus 2 pi, and then once you rotate this in the clockwise direction again, it will be theta minus 4 pi, then minus 6 pi, minus 8 pi, and so forth. Thus theta plus minus 2 pi plus minus 4 pi plus minus theta and theta plus minus 6 pi, theta plus minus 8 pi are basically coterminal angles. So now let's see what, in a generalized form, this is what you will write. This is the general angle for coterminal angles. So K, which is this K over here, can be, this K over here, it can basically be any natural number, and theta plus K into 360 degrees. So as you know, the 2 pi is basically 360 degrees in degree form, 2 pi is in radian form, and it is called the general angle, where theta is basically between 0 and 2 pi. So it can be anywhere in the circle. It can be this angle over here, it can be this angle, this line over here. And so basically, for example, if you had this line, it would just become, the theta would basically just be this. And if you just rotate this in one entire revolution where it reaches the same point, it will just basically be theta plus minus 2 2k pi. So now let's see the angle in the standard position. So an angle is said to be in standard position if its vertex lies at the origin of a rectangular coordinate system and its initial side along the positive x-axis. So this positive x-axis, basically this over here, is the initial side, and let's say this is the terminal side, and it lies basically in this rectangular coordinate system. And so let's say this here is another example. The angle over here is alpha, the angle over here is beta, and let's say this angle over here is gamma. And since we're taking this positive x-axis to be the initial side, so in this case alpha is basically this angle, beta is basically this angle, and this gamma is basically this angle. And then you also have this one which lies in this quadrant over here. So this angle is theta. An angle in standard position is said to lie in the quadrant if its terminal side lies in that quadrant. And in the above figures, so basically this one and the 3 that you have seen before, angle alpha lies in quadrant 1 as its terminal side is in quadrant 1. So let's just rewind back. See this angle over here? This is the first quadrant. This is the second quadrant. This is the third quadrant, and this is the fourth quadrant. And you can see that beta lies in the second quadrant, gamma lies in the third quadrant, and theta lies in the fourth quadrant. So yeah, that's just what it is. If the terminal side of an angle falls on the x-axis or the y-axis, it is called quadrantal angle. So it basically, if you have, let's say you have this rectangular coordinate system, and this axis itself is the terminal side, then it is, or let's say if it is here, or if it is here, or if it is here as well. If it lies on each of these lines, it is called a quadrantal angle, and that's basically just 90 degrees, 180 degrees, 270, and 360. So if the angle lies at this positive y-axis, if the terminal side lies on this positive y-axis, the angle is 90 degrees. If it lies on the negative x-axis, it's 180 degrees. If it lies on the negative y-axis, as you can see this angle over here, it's 270 degrees. If it lies on the x-axis, positive x-axis, the angle itself will be a full 360 degrees. Now let's see trigonometric functions and important results. So trigonometric functions, let's consider a right angle triangle with angle C is equal to 90 degrees and the sides ABCs as shown in this figure. So this is the 90 degrees angle. Oops. I'm sorry. Some glitching, but yeah, 90 degrees angle. And these are the sides A, B, and C. And these are just the points of the triangle, capital A, capital B, and capital C. Now, let m is less than a is equal to theta radian. So sine theta is basically equal to a over c. This is the angle theta, and sine theta is equal to angle a over angle b. So cos theta is equal to not angle a over angle c, sine theta is equal to the length of side a over the length of side c, and cos theta is equal to the length of side b over the length of side c, and tan theta is equal to the length of side a over the length of side b. That's really just it. So if you have to find theta, if you're given basically this length a and this length b, and if you're not given this length c, you can use this to find the value of theta. Basically, in this case, theta would be equal to sine inverse of a over c. So that's how you can find this angle theta. And same goes if you do not have this side A, but you have the length of C and B, you can use cos theta. And if you do not have angles, if you do not have side C, and if you have A and B, you can find theta by using tan theta. And you can also use cosecant theta, which is basically just the reciprocal of sine theta, so C over A. And you can use secant theta, which is basically just the reciprocal of cos theta, so C over B. And you can use cotangent theta, which is basically just the reciprocal of tan theta. And you can memorize this by seeing the third letter of each. So cosecant theta, the third letter is S, so it is the inverse of sine. And you can use the secant theta, so the third letter of secant is C, so that just means cos. Whoops, sorry. and the third letter of cotangent is T. So basically this means tan, and this is just basically a very good way to memorize what cosecant, secant and cotangent are. Important results are basically these. Cosecant theta is equal to 1 over sine theta. As I told you earlier, they're basically the reciprocals. Cosecant theta is basically the reciprocal of sine theta. Secant theta is basically the reciprocal of cosecant theta. And here is another one. Tan theta is basically just sine theta over cosecant theta. Cos theta, not cosecant. Cos theta. So cotangent theta is basically the reciprocal of tan theta. So basically this cos theta over here goes to the numerator, and this sine theta over here goes to the denominator, and then you have cos theta over sine theta. Now let's see the proofs of fundamental identities. So a square plus b square is equal to c square. So we already know this by the Pythagoras theorem. Now, because if you have, let's say this is a triangle, forgive my drawing. Let's say that this side is A, and this side is B, and this side is C. And we know by the Pythagoras theorem that a square plus b square is equal to c square. So a square, when you divide the left hand side and right hand side by c square, this is what you get. And so you can write down a over c square, a over c whole square as sine theta square, because obviously a over c is sine theta. And similarly b over c is cos theta, so b over c whole square is cos theta square, and that is equal to 1 because c square over c square is equal to 1. And that's how you prove this identity, that sine square theta plus cos square theta is equal to 1. Now let's see the other one. So again, the Pythagoras theorem that a square plus b square is equal to c square, and if you divide both sides by b square, you find out that a over b whole square plus 1 is equal to c over b whole square. And that just means that a over b, basically the opposite over the adjacent, is tan theta, and c over b is secant theta. So basically tan square theta plus 1 is equal to secant square theta, and that's how you prove the identity that 1 plus tan square theta is equal to secant square theta. And similarly, again, we have a square plus b square is equal to c square, and when you divide both sides by a, basically that just results in this identity that 1 plus cotangent square theta is equal to cosecant square theta. And well, that just proves all three identities. Now let's see the signs of trigonometric functions. If theta is not a quadrantal angle, so basically it does not lie directly on the axis. Whoops, wait a second. Yeah. So if theta does not lie on the axis, basically, then it will lie in a particular quadrant because, well, this equation that defines the magnitude is always positive. It follows that the signs of the trigonometric functions can be found if the quadrant of 0 is known, for example. Well, that just complicates things, but if theta lies in quadrant 1, then the point P, so basically the end of the line that defines theta, on its terminal side has both xy coordinates as positive. So basically if this, you have here a grid, and if the angle theta lies in this particular area, this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So if theta lies in this quadrant, then obviously the value of y and the value of x are both positive, and so that's that. So all the trigonometric functions are positive in quadrant 1. That is, remember, in quadrant 1 all the trigonometric functions are positive, and if theta lies in quadrant 2, then the x coordinate is negative and the y coordinate is positive, and basically the sine trigonometric functions are positive. Only the sine functions are positive in the second quadrant, and in the third quadrant the x and y coordinate are both negative, and the tangent coordinates are only positive in quadrant 3, and for quadrant 4 both the x coordinate is positive and the y coordinate is negative, and the cosecant not the cosecant well the cos coordinates are positive only in quadrant 4. And let's see. So find the sines of the following. Sine 160. So let's see. If we make this grid over here, 160 lies somewhere around here. This is the angle of 160. Whoops, just a second. Yeah, 160 degrees. So basically this angle lies in the second quadrant, and we know that the sine functions are positive in the second quadrant, so it is positive. Similarly, cosecant 190, that lies in the third quadrant, and we know that in the third quadrant only the tangent functions are positive, so cos 190 will be negative. And let's say we have tan 115, that lies in the second quadrant, and we already know that in the second quadrant only the sine functions are positive, so tan 115 degrees is negative. Now let's find the values of the remaining trigonometric functions. Find the values of the remaining trigonometric functions, where basically sine theta is equal to 12 by 13 and the terminal arm of the angle is in quadrant 1. Now remember that in quadrant 1 every single trigonometric function is positive. So whatever values you get ahead, they'll all be positive because the terminal arm of the angle is in quadrant 1. If for example it was in quadrant 2, then only the sine functions and the cosecant functions would be positive. The rest would be negative. So sine theta is 12 by 13, so cosecant theta is 13 by 12. Cos theta is equal to 1 minus sine square theta under root whole. So and this is from the identity that cos square theta plus sine square theta is equal to 1. So by using this particular identity, we can find the value of cos theta, and that just turns out to be basically 5 by 13. And again, it's positive because the terminal arm lies in quadrant 1. Secant theta is just the reciprocal of the cos function, so that's 13 by 5. Tan theta is sine theta by cos theta, that's another trigonometric identity, and basically that just means that tan theta is equal to 12 by 5. So cotangent theta is the reciprocal of tan theta, which is 5 by 12. Now let's see the proof of trigonometric functions. So we have this question: if tan theta is equal to 1 by under root 7 and the terminal arm of the angle is not the third quadrant, so it can lie in any quadrant except the third quadrant, find the value of cosecant square theta minus secant square theta over cosecant square theta plus secant square theta. So the third quadrant, remember in the third quadrant, the value of tan theta is positive. Only the value of tan theta is positive. Other functions are not. So it cannot, again, it cannot lie in the third quadrant. So let's see, tan theta is equal to 1 by 7. So obviously cotangent theta is the reciprocal of tan theta, which means that cotangent theta is under root 7. Secant theta, again, we'll use this identity to find the value of secant square theta. So secant square theta is equal to 1 plus tan square theta. So secant square theta is equal to 8 by 7. And cosecant square theta is equal to 1 by cotangent square theta, and that just means 1 plus 7, and so cosecant square theta is equal to 8. So we have found the values of cosecant square theta and secant square theta. Now let's plug those values in, and then we get 48 by 64, which is equal to 3 by 4. Now let's find the unknown using identities. So find x if tan square 45 is minus cos square 60 is equal to x sine 45 cos 45 tan 60. Now you can just plug in those values and just find x, because tan square 45 is basically just tan 45 whole square, cos square 60 is cos 60 whole square, and the rest is as it is. Now when you plug in the values, we obviously know that tan 45, you can use the calculator or just draw a triangle and you can basically just find the values that way. Tan 45 is 1, cos 60 is 1 by 2, sine 45 is 1 by under root 2, and similarly cos 45 is 1 by under root 2, and tan 60 is under root 3. Once you plugged in all those values, you can just perform the calculations, and basically eventually you'll end up with a value of x as 3 by 2 into under root 3. It's really just that simple. You can use a calculator or you can draw a triangle and find the values of each function. Now find the values of identities using an angle. So we need to find the values of trigonometric functions for 390 degrees. Now the way to find it, the value is very huge. It's beyond 360. So once it goes beyond 360, you basically need to find its equivalent, how do you say, its equivalent angle that is not beyond 360 degrees. What that means is basically if you have this grid and let's say this is 390 degrees. How is it 390 degrees? Well, because this is 360 degrees and then you have a further this degree. So this complete angle is 300 and just a second. The software is a little bit buggy, but just bear with me. So this here angle is 390 degrees. And obviously it goes beyond 360, the complete revolution. So basically what we need to find is this angle only. That is equivalent to 390 degrees. What is this angle? Well, you can use the formula of 2k into 180 plus theta. 2 into 180 is obviously 360. So 360k plus theta. This angle here is theta, this angle. And we need to find theta. So how do we find the value of k? Well, just divide 390 by 360. You get 1.08. And so let k is basically 1. 0.08 is the remaining. It is basically a value that defines this angle theta. So 2k 180 plus theta. K is 1. So 2 into 1 into 180 plus 30 degrees is equal to 390 degrees. Because 2 into 1 into 180 is 360. 360 plus 30 is 390. So you can use the value of 30 to basically just represent 390. Because after one revolution, after 360 degrees turn, it's basically the same thing. So theta is 30 degrees, so sine 390 is equal to sine 30. Why do we need this small value? Well, because you can just use this particular example to solve this question. So let's say this is an equilateral triangle, and so basically each side is, let's say it is 2, 2, 2, and 2. Each angle of this triangle is basically just 60 degrees. So this angle is 60 degrees. So is this angle. So is this angle, because it's an equilateral triangle. Once you actually divide this triangle in half, basically this side would be 1 and this side would be 1. And this angle is 30 and this angle is 60. So sine 30, so the sine of this angle is just 1 by 2. Which is why we have this 1 by 2. And so you can use the same property. So cos 30 is equal to under root 3 by 2. You can use the same triangle as you did before to get this value. So tan 30 is equal to 1 by under root 3, and cosecant 30 is just 2, because it is the reciprocal of the sine. Sine 30, and sine 30 was 1 by 2, so the reciprocal of that is just 2. So secant 30, the reciprocal of cos 30 is 2 by under root 3, and cotangent 30 is the reciprocal of tan 30, which is 1 by under root 3, so it is under root 3. Now let's prove the identity and find the domain. So prove the identity and state the domain of theta in each case. Well, the left hand side is tan theta plus cotangent theta. Now to prove that the left hand side is equal to the right hand side, you basically just take one side and use the identities that you learned before to prove that, and basically just convert one of the sides to the other side. So we're taking the left hand side over here. Usually, again, you take the side that has the most amount of functions being added up. So basically separate functions, cosecant theta, and on the one and on the other side there's just one big function in which many different trigonometric functions are being multiplied. That's hard to prove. The ones that are being added up are easier to prove, which is why we're taking the left hand side over here, tan theta plus cotangent theta, and we'll use the identities to basically convert this into this. So tan theta plus cotangent theta, you convert tan theta and cotangent theta into sin theta over cos theta plus cos theta over sin theta. Now you'll take the LCM. So sin theta will be multiplied with sin theta, cos theta in this numerator will be multiplied with cos theta, and we basically get this. Now remember the identity that sin square theta plus cos square theta is equal to 1. So basically now you'll replace that with 1. And this basically just turns into, once you take the reciprocal of this function, that just becomes, well, not the reciprocal of it, but we know that 1 over sin theta into 1 over cos theta. So 1 over sin theta is cosecant theta, and 1 over cos theta is secant theta. So that's how you've proven that the left hand side is equal to the right hand side. Now the domain of this function is basically just theta is any real number, but theta cannot be equal to any multiple of pi by 2, because sin theta becomes 0 when it is any multiple of pi, and cosecant, sorry, not cosecant, but cos becomes 0 when it is any multiple of pi by 2. And you know that 1 over 0 is undefined, so that cannot lie in the domain. So sin theta into cos theta can never be equal to 0, which is why theta cannot be a multiple of pi by 2. That also covers sin theta, because any multiple of pi by 2 eventually becomes a multiple of pi as well. So yeah, theta cannot be any multiple of pi by 2. Now, prove the identity and state the domain of theta in each case. So again, we need to prove that the left hand side is equal to the right hand side. Let's take the left hand side and prove that it is equal to the right hand side. We'll basically use the identity that secant square theta is equal to 1 plus tan square theta. So we'll replace this secant square theta with 1 plus tan square theta, and you'll use the other identity that cosecant square theta is equal to 1 plus cotangent square theta. So cosecant square theta becomes 1 plus cotangent square theta. And now basically, see, you've proven that the left hand side is equal to the right hand side by using the identities. And now you need to find the domain. Again, theta cannot be equal to, cannot be a multiple of pi by 2, because, well, you know that tan theta is basically just undefined at any multiple of pi by 2. And similarly, so is cotangent square theta. And now, let's see. Prove the identity and state the domain of theta in each case. Well, we'll need to prove that the left hand side is equal to the right hand side. So we'll take the left hand side, and basically now you can see that by using the algebraic identity that a square minus b square is equal to a plus b into a minus b. We'll use the same algebraic identity to see that secant theta plus tan theta into secant theta minus tan theta is equal to secant square theta minus tan square theta. And so you have this, and you can basically just use the identity that secant square theta is equal to 1 plus tan square theta over here. And so now you can cancel out this tan square theta and this tan square theta to get 1. And so you've proven that the left hand side is equal to the right hand side. And the domain of theta is basically just any real number because it just gives you 1. Now let's rationalize the trigonometric identities. Prove the identity and state the domain of theta in each case. Now, this is a little bit trickier than what we did before. We just used to plug in identities and things would just follow along as like butter. They would just eventually end up proving the equation. But this is just a little bit different. Let's take the left hand side. Now 1 minus sine theta over cos theta. Once you actually try to do this, just plugging in identities and stuff, you'll find out that it's really not that easy. Now there's a very simple way to do things like this. Basically you have something in the denominator which is cos theta. So what you can do now here is basically, you see the numerator 1 minus sine theta. Well, now you can just basically multiply it 1 plus sine theta over 1 plus sine theta. And this entire thing equals to 1, so it does not affect the value of the equation. But once you actually do the multiplication, this is basically what you call rationalization. This is the conjugate of the numerator. 1 plus sine theta is the conjugate of 1 minus sine theta, and you take the conjugate on both the numerator and the denominator and multiply it with the original expression. What that does is basically this 1 minus sine theta into 1 plus sine theta becomes 1 minus sine square theta, using the algebraic identity that a square minus b square is equal to a plus b into a minus b. And so that's how you get this. And in the denominator, cos theta is just being multiplied with 1 plus sine theta, and 1 minus sine square theta is equal to, using the identity, it is equal to cos square theta. The identity that cos square theta plus sine square theta is equal to 1. So cos square theta is equal to 1 minus sine square theta. So you have this now. And what you can basically do is, this cos square theta will be cancelled. The one of the cos square thetas, the cos square theta over cos theta is equal to cos theta. So basically you can cancel out this cos theta and the 2 from this. And so you get cos theta over 1 plus sine theta, which is the right hand side. And the domain, well, the domain is basically all real numbers, but theta cannot be equal to 2n plus 1 or into pi by 2. Why can it not be equal to 2n plus 1 over pi by 2? Well, because the denominator can never be 0. Because once the denominator becomes 0, the function becomes undefined. Anything divided by 0 is undefined. And basically 1 plus sine theta cannot be equal to minus 1, because 1 minus 1 is basically just 0. So how is 1 plus I'm sorry, this has been a mix up over here. Basically 1 plus sine theta can never be equal to 0, because the denominator cannot be equal to 0. So sine theta cannot be equal to minus 1. When is sine theta equal to minus 1? Well, when the value of theta is 2n plus 1 into pi by 2. This n can be any integer, any natural number, basically 1, 2, 3, 4, 5, 6, 7, 8. And once you plug in, say 1 instead of n, so that just becomes 3 pi by 2. The value of sine theta at 3 pi by 2 is minus 1. Similarly, when the value of n is 2, it becomes 5 pi by 2, and again the value of sine theta is minus 1 at 5 pi by 2. So yeah. So let's solve the trigonometric equations by LCM and squares identity. So prove the identity and state the domain of theta in each case. This is a big equation, and we need to prove that the left hand side is equal to the right hand side. Again, we take the side that has the maximum amount of terms and basically just minimize it into the one with the less amount of terms. So now we'll take the left hand side because it has more number of terms, and we'll need to prove that it is equal to the right hand side. So how do we do this? Well, we'll take the LCM. So basically cos this, the numerator on this side will be multiplied with the denominator on this side. So cos theta plus sine theta will be multiplied with cos theta plus sine theta, and the numerator on this side will be multiplied with the denominator on this side. So cos theta minus sine theta into cos theta minus sine theta, so which is why you have this in the numerator and now this in the denominator once you take the LCM. So cos theta plus sine theta whole square plus cos theta minus sine theta whole square over cos theta minus sine theta into cos theta plus sine theta. Again, I don't really tell you how to take the LCM, it's just basic maths. So once you expand this, you basically get this big expression. The denominator just becomes cos square theta minus sine square theta by using the algebraic identity that a square minus b square is equal to a plus b minus a plus b into a minus b. So yeah, that's how you got the denominator, and the numerator, well, that's just basic square expansion, and so you get this. Now you can basically just cancel out this and this, the 2 sine theta minus 2 sine theta cos theta terms. One is positive, one is negative. You'll just cancel them out, and now you basically get this. How did you get this? Well, 2 cos square theta plus 2 sine square theta. Well, this sine square theta term and this sine square theta term will be added up, and this cos square theta term and this cos square theta term will be added up to give you 2 cos square theta plus 2 sine square theta. And in the denominator, you can replace this cos square theta with 1 minus sine square theta by using the algebraic identity that cos square theta is equal to 1 minus sine square theta. So yeah, this term, this cos square theta becomes 1 minus sine square theta. And now you basically get this again, and you can take the 2 common in the numerator to get 2 into cos square theta plus sine square theta, and this minus sine square theta minus sine square theta becomes minus 2 sine square theta. Now cos square theta plus sine square theta is equal to 1. So now 2 into 1 is basically just 2, and because this expression just becomes 1, and 1 minus 2 sine square theta remains as it is, and that is basically just the right hand side in the equation given to us originally. And now the domain is basically theta is any real number, but theta cannot be equal to 2n plus 1 pi by 4. Why? Because again, the denominator cannot be equal to 0, and basically this means that the value of 2 sine square theta cannot be equal to 1 because 1 minus 1 is equal to 0. So 2 sine square theta cannot be equal to 1. So sine square theta cannot be equal to 1 by 2, and basically the value of sine square theta is, just to make it a little bit more easier, let's just say sine theta cannot be equal to 1 over under root 2, and you can basically find out that this value when basically 2n plus 1 into pi by 4, when you plug in that value into theta, that just gives you 1 over under root 2. So basically when the value of n is 1, 3 pi by 4, well, at 3 pi by 4 the value of sine theta is 1 by under root 2, and if the value of n is, let's say, 2, 5 pi by 4, well, 5 pi by 4 is also equal to 1 by under root 2. So any real n can be any natural number, and once you plug in that value, you get a value of theta that gives you 1 by under root 2 when it is in sine theta, and in general that just means that the denominator over here becomes 0, and so that is why it is not in the domain of theta.